Welcome to Drone Systems and Control course. In this particular lecture, we are going to talk about state space representation of the multi-rotor system, and we are going to analyze from that perspective. Right? So, what are the objectives? We are going to understand the concept of state space. We are going to develop the state space model for linear time invariant system, input output relationship. We may consider simple mechanical system to show how it can be derived, right. We can understand the block diagram representation of linear time invariant system. We learn to convert the state space representation system to transfer function representation, right. So, any system when you look at it, right, there is a system, a disturbance is present externally, there is an external input R which goes in, you have a response Y. You measure the system response and you have a feedback controller. Based on the response, it computes what is the change in input required, right. If you look at the input variables, there are three variables. One is external input, manipulative variable which is U, and disturbance or noise which comes in externally present to the system, right. The output variable, the variable of our interest to be measured. If you take a typical drone subsystem, what we are talking of, the multi-rotor system is what we are looking at here, right. This is a system. I am trying to give a desired altitude. Let us say we are going to climb. I am talking about desired altitude as an R. Actual altitude is just I am measuring as an output which come from the LiDAR, right. I can measure that along with other variables. I can pass on to a controller. It could be a Jetson Nano, or it could be even a Pixoc, or it could be a microcontroller which is being there, where the control feedback control law is being implemented. The output is an actuator command which goes to your motor and change the motor speed, and you control the whole system. Yes, right. Now, what is state of the system? Let us look at some definitions. First, let us define what is the state of the system. It is the minimum information needed about the system in order to determine its future behavior, right. What I meant is, given the state of the state at time t naught, okay, together with the input at time t greater than t naught, you can determine the output for any time t which is greater than or equal to t naught, right. Now, if I talk about state variable, it is the smallest set of variables along with the input variable to the system that is required to determine the output of the system. That is what we call as a state variable. State vector, if I put all these variables, right, it is an n dimensional vector whose components are n states variables that completely describe the system, right. Now, if I talk about state space, it represents set of all possible states of the system in all axes corresponding to the state variable x1 to xn, right. Why state space approach? We can have a systematic analysis and synthesis of higher order system without truncating system dynamics. If you look at transient analysis, we talked about transient analysis, right. We are interested in truncating the system to second order so that we can interpret and appreciate how speed the system responds, how the smoothness of the trajectory and everything, right. But if I want to do it for higher order system, for multiple input it will become very difficult. That is why I prefer to go into state space representation. It is more suitable for multi input, multi output systems, right. It is a uniform platform for representing, right. It could be time invariant system. Think about it, you have a drone with a battery powered, right. The mass remains constant, right. Time variant system, same drone, instead of battery I am carrying a fuel, right. You are consuming a fuel to generate a power. The mass of the fuel is going to deplete over a period of time. It means the total mass of the system is going to change, right. And just give you an example, right, time variant system. It could be nonlinear system, right. It has a standard form x dot is equal to f of x comma u, or it could be a linear system. It can be represented x dot is equal to ax plus b u, right. I have a uniform structure to represent all these systems, right. I can describe the dynamics of almost all the system, mechanical, electrical, biological, economical or social. I can represent them in this form. Okay. The transfer function representation are valid only for linear time invariant system, remember that. Okay. Now, what are the factors generally influence selection of the state variable? I am looking at a minimum number of first order differential equations required to describe the system completely. Too few variables will not be able to describe the system completely. Too many variables increase the computational complexity and leads to loss of controllability and observability. We will talk about controllability and observability in later part of the lecture, right. The state variable should be linearly independent. Without linear independence, may not be possible to solve all other system variables, not possible to write the complete state equations, right. Now, how do we select these state variables? The number of state variables is equal to order of the system, right. It is equal to number of independent energy storage element present in the system, right. If you take a typical spring mass damper, right, you have two energy storage, your spring and damper, right. I can have a same spring, I can put it in parallel or I can put it in sequential. You can define your state variables based on how many storage elements that you have, right. Is there a restriction on selection of storage variables? Yes, all state variables should be linearly independent. They must completely describe the system, right. That is a very important requirement. Now, general state space representation, right. A generic system. I am looking at a generic nonlinear system, right. There are n state variable x1, x2, xn, right. x1 dot is equal to f1 xut. Similarly, xn dot is f at xut, right. I am talking about there are r input u1, u2, u3, u4, ur of t, that is my input vector. I have a system which is described by n state variables x1 to xn. I have output, there are m output which is going from y1 to ym, right. State vector, when I say the bold x represents all the n states, right, x1, x2, x3, xn. Input vector, the bold u talks about all the r inputs. Output vectors y, bold y, we talk about all the m outputs, right. Here n, r, m are the number of states, input, number of output variables respectively, right. So, let us look at a first order differential equation with the constant coefficients, right. So, x1 dot I am looking at, instead of nonlinear I am going into linear time invariant system, right. So, x1 dot is a11 x1, a12 x2, a11 xn. It depends on all n states in a linearly and depends on the input also in linearly b11 to b1r. Similarly, xn will have an1, an2 x2, ann xn, b1 n1 u1, bnr ur. I can represent in the matrix form x dot, right, d by dt of x1 to xn. If I just represent in matrix form, and I have a matrix A which are all the coefficient a11, a12, an1, an2, ann, and then the state vector. Then I have a B matrix which comprises of the linear coefficient with respect to the input b11 to b1r, bn1 to bnr, u1 to ur. That is your input vector, right. Similarly, you can write linear representation of your output, which is again a combination of C1 x1, C1 to x2, C1 xn for y1, and depends on input d11 u1, d1r ur. I can represent the same in a matrix form. My y vector is C matrix times state vector plus D matrix times your input vector. So, I can represent in a nice form state equation x dot equal to Ax plus Bu, right. So, for example, if I am taking a second order system, right, x1 and x2, there are two state variable x1 dot equal to x2 dot, which is a11, a12, a21, a22, x1, x2 plus b1, b2 and u. Single input I am talking of here, right, for ease of understanding. X is a column vector of length n, u is a column vector of length r in a standard definition. Then the A matrix will be n cross n, it's a square matrix. B matrix will be n cross r, right, that talk about the weights of the inputs. In our case, if you take a second order system, your A matrix is a 2 cross 2, your B matrix is 2 cross 1, because we are talking about one input. Output equation y equal to Cx plus du. Suppose I am talking about altitude or yaw rate as a response, I am talking about C1, C2 of x1, x2 and dut, right. Y is a column vector and C is the matrix, again m cross n, D is a m cross r matrix, right. Now, let us look at our yaw subsystem again. If you remember, in the transient response we talked about linear approximation at the equilibrium point, how to derive this yaw subsystem. The differential equation can be represented, r dot is yaw rate, nrr, n omega omega d, nvvd, omega d dot is trr plus t omega omega d plus tvvd plus t theta theta d, right. I can represent them in a state space form, r dot and omega d are my states, then nr n omega, tr t omega becomes my A matrix and my state vectors are r and omega d, my input are vd and theta d and this is my P matrix. I can represent them nicely in AB. Assuming the theta d is going to be 0, then it becomes a single input system. This, if you look at x dot is equal to Ax plus Bu, right. And y, what is my output I am looking at? Yaw rate is my output, then it is 1 0 r and omega d, right. So, I can represent this, my C matrix is a vector 1 comma 0, right. I can represent them in a nice state space form, but I can also represent them in a nice block diagram, right. If you look at how my input multiplied by NV, which is coming in, and it also depends on NRR, right, and N omega d, right, that goes into integration of that. Well, that is my R dot equation. If I integrate, I will get R, and that is my output I am getting, right. I am just saying that omega d, my output equation, if you look at my y is 1 0 r, which means 1 times r, the r alone I am just looking at, it is not depends on omega d or it not depends on Vd. So, I can write it in a block diagram form to understand, right. A typical mechanical system, again, to connect it so that you can appreciate, I can take a spring mass damper, right. I can apply a Newton's law, I can say mx double dot equal to remaining forces, which is depends on damping and your spring, right, and external force. I can equate, I can get a typical second order equation, mx double dot plus bx dot plus kx is equal to f. Now, I can write them in a standard form, x double dot is b by m x dot plus k by m x is f by m. Now, I mentioned earlier, if you want to pick up the state should be energy storage element. There are two energy storage element here, one is a spring, other one is a damper. I can take them as a state, x1 and x2 there are two state, x1 depends on the displacement, the x2 depends on velocity, that is x1 is x, x2 is x dot, right. If I am just going to rearrange the differential equation, x double dot equal to minus b x dot minus k x m x plus f of m, basically I am bringing these two terms to the other side of the equation, right. Then if I am going to substitute x1 dot, x1 is x, x1 dot is x dot, which is nothing but x2, x2 dot is, x2 is nothing but x dot, x2 dot is x double dot, right. That will become minus b m x2 minus km x1 plus f of m. So, I can use this and represent them in a typical state space form. X dot is equal to this, right, and let us say I want to get the displacement as an output, then y is equal to c into x, right. Then A matrix is this, B matrix is this, C matrix and D matrix. So, you can represent them in any state space form you want, right. Now, if I am going to do it state space representation of generic ordinary differential equation, treat every derivative as a first order derivative, right. Let us say dx square by dt plus b by m dx by dt plus k by m x and fm, right. This is already a first order derivative, right. It can be written, the second order can be written dx1 by dt, which is basically dx square by dt, whereas dx by dt is x1. So, you can use from ordinary differential equation also, you can convert them and represent in a state space form nicely, right. You can bring them into x dot is equal to ax plus bu and y equal to cx plus du. Now, I can convert the state space representation to Laplacian form, right. I can take a Laplace transform assuming that 0 initial conditions, then c x of s, s into x of s equal to ax of s plus bu of s and y of s equal to cx of s and du of s, right. I can rearrange this x of s, sx of s minus ax of s equal to bu of s, right. Then I can take x of s out, s is a constant Laplace operator, s into I is identity matrix minus a into x of s equal to bu of s, right. Then x of s is, I can take the multiply the both side of the equation with the inverse si minus a whole inverse into bu of s, si minus a whole inverse and si minus a will become identity, that is where you will have x of s alone, right. Similarly, I can substitute the output equation, y of s is c x of s plus du of s. If I substitute x of s in this y of s equation, c into xi minus a whole inverse into b plus d into u of s. The transfer function is nothing but y of s by g of s. So, I can get the transfer function, which is nothing but c into si minus a whole inverse into b plus d. So, I can get this transfer function from state space also, right. So, if you remember, we talked about yaw dynamics, right. We represented them in a typical second order system, r dot and omega d. This is my A matrix, this is my B matrix, right, and this is my C, right, D is 0, right. If I am trying to take y of s by u of s, which is nothing but C, si minus a whole inverse into b plus d, right. Now, remember d is 0, if I substitute a, b and compute this, you can try it out, right. You get a typical r of s by v d of s is a transfer function of this form, okay. Now, in a summary, we talked about state space representation. How do we represent time varying system, time invariant system, nonlinear system, right. It is very uniform for everyone. We talked about how to define the state variables, and state variable should be equal to number of independent energy storage elements, right, and the state variable should completely describe the systems. We talked about that, and state space can be used for any typical multi input multi output system too. We can use it for any higher order systems. We talked about if it is a differential equation from a different ordinary differential equation, how do we convert the ordinary differential equation to first order ODE, and using the first order ODE we can write the state space also, right. We also talked about for single input single output system in a state space form, how do we get the transfer function and vice versa, right. That is the end of this lecture. You can go through this modern control engineering or GATA to know more about how do we represent the state space system for various others subsystems, electrical, mechanical systems. If you want to understand how do we do it, and you can refer to their feedback control system book also. One of this will help you to understand many examples and practice. Thank you.